Hello and welcome back to Calculus 2. Back because we already did the first lecture. It's not a lecture, it's a review of things you need to survive this course. Now we are starting with the lecture number 1, lesson number 1 on area between two curves. We want to calculate the area between two functions. We are going to learn two formulas that will help us set up the problems. And then we are going to use, obviously, Calculus 1 integration, whether it's 4, 9, 5, 2, or 5, 5, to solve the problem, whatever is necessary. So either definite integral or the u sub with the definite integral. So before we go into area between two curves, let's review Calculus 1 area under single curve. And that's technically 5 two definite integrals. If you have some kind of a function, f of x, in the xy coordinate system, you can find area under the curve as long as the function doesn't dip below x-axis. If it goes below x-axis, it creates negative area, and then the numbers become wrong. So you have to chop it up into parts and use absolute value to bring the negative numbers up and so on. That's something that you learn in Calc 1. Now what we are concerned here with is that you are going to have a part of this function that you are interested in terms of area. And that's this shaded piece. This shaded piece happens between x1 equals a and x2 equals b. So those are the two values. And you are integrating, meaning you are computing the area by integrating the function between these 2 points a and b. So area is defined, I'm going to do this in blood actually. Area is defined as the integral a to b, and those are your x1 and x2 limits, of the function f of x times dx. F of x produces the height, dx produces the width, and f times x over here in this case is going to be the area under the curve. Now what is this dx? If you draw what we call a representative rectangle, which you might have ignored in Calc 1 and now is going to be your lifesaver. If you remember in Calc 1 you took the area, and to approximate the area under the curve you divided into rectangles and you computed area of each one of those rectangles. You remember that? Maybe. Yes, Riemann sum. Now, this one that I draw here is the infinitely thin rectangle that you learned about as a Riemann sum, right, in Calculus 1. So this representative rectangle has all of the features of a rectangle that you think, look, it's touching the function f of x, so its height is f of x. If it's here, it's higher. If it's here, it's lower. If it's here, it's higher, right? So it follows, the top of this rectangle follows the function on top, which means that f of x will always produce the height of that rectangle. The dx is the width. You know that one as delta x from before, which was b minus a divided by the number of rectangles you have, and so on. We don't use that now, but important thing is that this dx is the same as that delta x from Calc 1. And that's this puppy here, dx. So you have height, f of x, times the width, dx, and you get the area. Height times width, right? Area. We don't need this. Just a formula. So if you want to calculate the area under the curve, well, we had it in the previous with the review. I'm going to go back to the review real quick and remind you that we found this area here by integrating the function from 3 to 5, and here is the pretty much right? The same graph as I have over there, except it's not wavy. Now it's a straight line. And we calculated 16, and we counted 16 units squared to actually be the correct answer. Now, the functions obviously can be anything. You can do square root of x, you can do ln, you can do trig, you can do, right? All of these things. The goal for today, for Calc 2, is to teach area between two curves. You see that your bottom is flat over there, right? It's x-axis. But what happens if you have a function on top and then another wavy function on the bottom? This formula will not apply anymore because the formula only accounts for f on top. But you will have another function on the bottom, call it g of x. So clearly this formula doesn't fit anymore. So for this situation now, when I go to Calc 2, let's say I have some function f of x over here, and then let's put the g of x, let's say like this, g of x. I'm going to put g of x somewhere else, right here. And I have this shape that I'm looking to calculate the area for. So that's y, that's x, good old. Well, the first thing is to understand that this shape stretches left and right as far as intersections go. So there is an intersection right here, which gives you a, and there's intersection right here, which gives you value b. Guys, those are your a and b on the integral. And the question is, how do we get those? Well, you get those when you set f equal to g, because they share the same y value. They share the same x value. So by equaling the two functions to each other, you will get x equals a and x equals b as answer. So here in blood, to compute a and b, set f of x equal to g of x. That's your first order of business. Because when you write integral a to b, you better know what a and b are. Now, sometimes those are given, and sometimes you have to find them. If they're not given, you will set a equal to b, and you will calculate those. I mean, you will set f of x equal g of x, and you will calculate a and b. And now, what's the rest of the formula? Well, let's do a little, I'm going to draw another picture, because I don't like that. It doesn't matter that it dips below, but it's hard to explain it when it dips below. So what I'm going to do is I'm going to make this G shallow so it doesn't dip below. It's still the same picture, it just doesn't dip below the x-axis. It's just easier to explain. It doesn't matter. You won't have to worry about negative areas. That doesn't happen for these two. You'll see why. So here we go. Where do we start? The first order of business is for me to draw these vertical lines here to kind of section off this part. The function that it's on top is f, and the function on the bottom is g. Would you agree that if you take integral a to b, let's actually color code it. How about blue? A to b of f of x dx, you would calculate all of this?
Yes.
By Calc 1, right? Sounds good? Good. And now, let's go purple. If you calculate integral a to b of g of x dx, what do you calculate?
Everything below g of x.
Everything below g of x. So I'm just going to shade it this way. What is that you need? Yep. You need this piece. And how you get this piece? You get it as a blue minus purple. That piece is blue minus purple because blue stretches from the top all the way to the bottom, and the purple is just the piece you don't need. How about we think about bananas for a second? When you purchase a banana, you get the whole unit with a peel, right? There is a piece that you want to eat, which is the pink one, and there is a piece that you're going to throw away, which is the one on the bottom. So when you take the banana, you peel it, you throw away the peel, you eat the banana, right? So the idea is to subtract these to get the area between two curves. And in Calculus 1, there is that theorem that says that if they have the same limits, you can put them into a same integral, which creates the formula that you guys are learning. Area between two curves, a to b, f of x minus g of x dx. Now, some students like to remember this formula as integral of top minus bottom, meaning function on the top, in our case f of x, function on the bottom, g of x, so top minus bottom. You set f equals to g to calculate your a and b, and then you put both of those into the integral and you compute the values. And that's it. I hope you're not disappointed. So now, this is your first formula of the semester. These formulas are not provided on a note sheet for the test, obviously, because this is all you learn. That's it. That's your Calc 2. If this formula is given on the test, then what are you tested on? Ability to integrate from Calc 1? Right? Makes no sense. So this is what you're learning for Calc 2, this particular formula. That's what's new. So now let's take a look at examples of this. Say you have a case of, let's make up a parabola and a straight line. Those would be simple to compute. We'll probably get to the really disgusting numbers, but that's okay. We can deal with numbers. So let's say you have parabola 1, 2, 3, 4, 5, 6. So parabola drops down like so. Let's say that's y equals 6 minus x squared. All right? 6 minus x squared. And let's pick a line How about y equal x? It's fine. It's a 45-degree line. Y equal x. And we are interested in area between these two curves. Unfortunately, parabola is a curved line. Curved line will not allow us to calculate the squares exactly, so we can't calculate exact area unless we do the integral. You can approximate very well, especially because y equals x goes through half of those squares on the bottom, so it's easy. This is why you should have a square paper, guys, for your math and physics courses. Square paper, and engineering in general. Now, I'm going to, first what I see, what's A? 0. You see that on the picture. I don't have to do intersection to calculate A. It's clear. A is 0. Because I did not shade anything left. Guys, I'm going to erase this, so don't draw this. Look, this parabola will continue this way. This line will continue this way. They will have another intersection there, which would spawn a point on the x-axis. And in case that I had the full picture, that would be your A, if I shaded everywhere through. But I didn't. I only took up to here. So my A is equal to 0. I don't have to compute it. But I do have to compute this B. B is unknown. So I still have to set these two equal to each other. Well, such is life. Let's go. My function f, which is the one on top, is 6 minus x squared, no coughing, and g is the one on the bottom, which is x. To find a and b, I will set these two together, to each other, but I know that a is 0, so I don't have to worry about it. I'll just calculate. So 6 minus x squared is equal to x. Move everything to the same side. X squared plus x minus 6 equal to 0. And we can factor this. Woohoo. X plus 3, x minus 2 equals 0. X is negative 3, x is positive 2. So what's b? B is going to be positive 2. We use a little bit of common sense over here because one value is negative, one value is positive. If, remember how I completed the picture earlier? If it was a full picture, your A would be negative 3. But since we are only using the half of it, it's not a half, it's the right part. We only have x equals 2 and x minus 3. We're just going to drop that for in this case because we don't need it. We have a to be 0. Okay, time to set up the area integral. So your Calc2 learning is figure out a and b. And now integral 0 to 2. 6 minus x squared is on top, minus x on the bottom, all of that in parentheses times dx. Bueno? See, okay. And now we integrate and compute using Calc1. 6x minus x cubed over 3 minus x squared over 2 calculated from 0 to 2. You plug in 2 everywhere minus plug in 0 everywhere. Well, in this case it's polynomials, so 0 is going to kill everything, so we just have to worry about 2. That's going to be 12 minus 8 thirds minus 4 divided by 2 is 2. So this is 10 minus 8 over 3. The common denominator is 3, which is 30 minus 8, which is 22 over 3. over 3? Are we all agreeing with that? No? Yes?
Are we only plugging in 2?
Well, you plug 0, everything is 0, right? You can do that when you have cosine and e, right? E to the 0 is 1, cosine of 0 is 1. So you have to be careful. For polynomials, you plug in 0, everything dies, you'd be good to go. Okay, should we check this? Let's say you care and you want to check. Now, this picture is not going to be the greatest, but 22 over 3 is roughly 7, right? So I should have about 7 of those squares in there. If you graphed nicely on a square paper, which is why I'm telling you square paper saves your life here, you should see about 7 squares. Now, this is not going to be the greatest because I did not graph x coordinate exactly for the parabola. The x coordinate for the parabola is the square root of 6, Square root of 6 is about 2.3 something, 2.4 something, whatever. So you should cut through here, actually, not through there. So that's why it's not going to be precise when I draw this. But I'm going to erase this. But if this was the case, for the parabola, we need to count 7 squares in the shaded region. And you have 1, 2, 3, 4, 5 full squares, and then these 2 halves on the bottom makes a 6th square, and then the 7th square from these pieces that are on a side, and you see it kind of adds up, right? This is the great thing about math. And as you can see over here, one of the first rules of engineering, draw big so you can see it, and then do it on appropriate paper so it actually makes sense, right? So you can actually verify what you did. You will be able to do this 100% of the time to check your answer, that your answer is right in a range where it should be, if you have a correct graph on a graph paper. Obviously, if you don't care about this, don't worry about it. So that was a sketch just for us to kind of verify this a little bit, and we did calculate the exact area of 22 over 3, which is area between those 2 curves. Now what I'm going to do is I'm going to introduce you to a sideways problem. Say you have a sideways parabola looking like this, and then let's go with the line like here. And you want the entire area, so I'll shade this slightly right here. You want the area of this. So let's put some values here. 1, 2, 3, 4, 5, 6, 7, 8. So this over here is 8. And we already said that this line is y equal 2x. This is where Calculus 2 gets tricky. Remember how I talked about representative rectangle? That one will save your life in this course, and especially Calc 3. You need to be able to use it. Representative rectangle dx is a vertical, infinitely thin rectangle that stretches from the bottom to the top. Let me draw that representative rectangle here. You label it as dx. Holy nightmare, this is a powerful thing. Please put your pens and pencils down and look how this takes care of all of that. Representative rectangle has a top and a bottom. Observe that the top is always riding f of x function, which is the function on top. The bottom of the representative rectangle always rides linear line in this case, which is the bottom function. Top of the rectangle minus the bottom of the rectangle. The rectangle takes every position from A to B. And no matter how short, right, it has to fit in between, it has to be vertical. Anytime, right, you move the rectangle, it picks up the top, rides on the top function f, bottom rides on the bottom function g, and it's always f minus g, top minus the bottom. This one, the top of the representative rectangle, I don't care where you draw. You can draw it here, you can draw it there, you can draw it there. Anywhere you draw, representative rectangle, the top of that rectangle always rides f of x. Bottom always rides g of x. Left and right happening from A to B, which are these puppies. And it's a dx that did that. You see that? All of the features of the formula in one spot with the dx representative rectangle. That representative rectangle moves around. So students generally like, and I did the same thing, like to think about dx swipes from left to right, from A to B, riding these functions. So it starts really big and then it kind of keeps diminishing in this case, right, going like that, which is kind of cool. That is the story of representative rectangle dx. Look at my new problem here. If I draw representative rectangle dx, something terrible happens. Can you tell me what happens? Well, that's not terrible.
F of x minus f of x.
That's it. He said f of x minus f of x. You see that, is this the same line? Coming from the same, it's not a function, but let's say function. Is it? So when you subtract it from itself, what do you get? 0. dx doesn't work. Dy. Yes, see? Draw dy sideways, like that. If you draw dy between values of c on the bottom and d on the top, which serve as your a and b now, if you draw dy, do we all see that the right side of dy always rides parabola and the left side of dy always rides the linear line as the dy goes up from C to D? Do we see that? Representative rectangle, left side always rides the linear line, right side always rides. And as the representative rectangle takes on all of the values, it's always the case that the left sits on this line and the right sits on that line, which tells us that now we can write the same formula for sideways problems that must use dy as area equals integral c to d, because those are y values. And now we're going to have f of y minus g of y dy. Limits are y, functions are in terms of y, dy at the end. So everything in respect to x or everything in respect to y. No mixtures. That's for Calc 3, okay? So everything in respect to x and everything in respect to y. One or the other. No mixtures. So this would be your sideways. It's the same formula, it's just sideways. Students like to remember this as right minus left. Right minus left. Yes?
By mixture, do you mean like there won't be any where you have a segment of it that you have to use the vertical rectangles and the segment that you have
No, the mixture, you could have that.
Okay.
The mixture in terms of that you put y limits dy, but these are in terms of x.
Okay.
You can't have that. Everything 100% in terms of y or everything 100% in terms of x. What you asked for would be some kind of honors capstone things that I can come up with like this, and then if you're requiring that, I'll supply you with the interesting example. Let's call them interesting examples. Okay. All right. So we have right minus left in this case, which, guys, if you were to grab this and just like straighten it up, right? This would be on top, And that would be your f of x minus the bottom line, right? So if you are to turn this, that formula becomes the x formula the same way you have it. So this problem works out the same way as the previous problem. Now observe that I did not cut half of it like I did last time, not half, but part of it like I did last time. So now we get to do the full problem here looking at these lines. I have my function here. This is what pre-calculus kicks in. If you have something like this, that's going to be y equal x squared. If you have something sideways like that, it's going to be x equals y squared. So to figure out this equation here, we will write x equals 8 minus y squared. So that's our equation, following what you learned in pre-calculus for sideways parabolas. They're not functions, but if you have a y as a variable, they become sideways functions because it works that way.
How do you know it's not? Oh, never mind.
The positive opens up and the negative opens down. If you are to stand this up, it will be opening down, so it's negative y squared. So 8 minus y squared. See, this is the positive y squared, and it opens up to the right.
Oh, okay, got it.
This one opens up to the left, so it's 8 minus y squared. I mean, negative y squared plus 8, but we just write it this way.
Oh.
We have same procedure for area between two curves. Set the two functions equal. Calculate your C and D in this case, because A and B are for x, C and D are for y. Okay, so we have a little issue here, guys. This function is x equals everything else. This function is y equals everything else. So clearly, we have to flip this function. So this function will be changed into x equals y over 2. And now we can set them equal. Y over 2 is equal to 8 minus y squared. And now y squared plus y over 2 minus 8 equals 0. And now 2y squared plus y minus 16 equals 0. We good? Now you need to solve this equation. What are the options you have? If we can factor, we factor. Quadratic equation is one of them, right? The negative b plus minus square root of, right, all of that stuff. Essential oils is another one. Or you can select it like this and then push math over here. Select action. Solve for y. And there you go. You get the answers. It's really easy. You know, math is a joke, right? Oh, come on, give me decimals. Why you give me this stuff? Okay, fine. You win. You win because I really don't want to do this. Y equals square root of 129 minus 1 over 4. And that is actually going to be your D, because that's the larger number. The other number is y equals negative square root of 129 minus 1 over 4, and that's going to be a C, because that's a lower number, right? C number is always lower than the other one. So you use the formula to calculate this: negative b plus minus square root of b squared minus 4ac divided by 2a. and then you just shovel through all of these numbers, and you eventually get these values. Now, I would like to know the decimal values for this, and is there anyone who actually invested time in life to do this?
$2.59 for the positive one.
2.59, thank you. I'll call that 2.6. How about that? So that's our D.
And negative 3.089 for the...
So 3.1 for the C. Thank you. Great. So now we are going to have our area to be the integral from negative 3.1, kill me now, to 2.6. And we are going to have right minus left in terms of y's because it's going to be dy. So I have 8 minus y squared minus y over 2 dy. Right minus left. And now we have at the end 8y minus y cubed over 3 minus y squared over 4, calculated from negative 3.1 to 2.6, which is going to be equal to a number, and we're done.
So in this case, since we're doing it in respect to y, would we take the y that's further along on the x-axis?
I'm sorry?
Will we use the y that's further along on the x-axis to act as the larger?
Yes.
That's why, okay.
But here's what we, can you repeat the word you used?
Since we're doing it on, we're using the y that's further along.
That's the word. Can you say that F word again?
Further?
Further, thank you. Guys, you've seen that meme when they have a small brain and then the bigger brain and the bigger brain, then the lit up brain when something is amazing? All of the formulas here are going to have those levels, okay? So you know that lit up brain? It's not to remember X formula and then the Y formula and then maybe Z formula and then whatever. It's to remember that it's no matter which dimension you're working in, it's always further away minus close by. Both of these formulas, for X and for Y, work that way. Look at this. dx, and this is your x-axis, further away minus close by. Of what? From x-axis, because we're doing dx. So dx, x-axis, further away minus close by. Then you move to your y case, dy, y-axis, further away minus close by. So technically both of these formulas are the same concept of further away minus close by. Now, what is the issue of memorizing top minus bottom? The issue appears if the problem looks like this. This is where further away minus close by saves your bacon. Because this would be F, this would be G, because it goes further away minus close by, and that will give you this. That's the trick, to learn the form, not just, So top minus bottom, it's pretty much going to work for every problem unless someone is really trying to trick you. And the same thing for right minus left. It works pretty much because we just put lame problems all the time. But if you have something more interesting like this, then top minus bottom doesn't really work. It's actually further away minus close by. So that was excellent. Excellent question, and it led into this discussion. Yes?
How would you determine which one to put first if it looked like they were pretty much equidistant from the x-axis?
You can't have them equidistant from the x-axis because there will be no difference between them. One has to be higher than the other, or one has to be to the right or to the left in order to have the difference between them. If they're at the same level, they will be the same function, and they will be, so they can be on the equidistant. You can have sine and cosine, right?
But if they like kind of relatively appeared that way, so like at first glance at the graphs, you couldn't really tell which one was further.
Well, there are some features. You're either looking at the formula. For instance, it's not humanly possible to make a great distinction between 2 to the x and 3 to the x, but carefully graphed on the square paper, you will know which one is which.
Okay.
Or with a software graph, you will know which one is which. There is always going to be the difference between them because they cannot be the same function, which is why there is a difference between them to find the area between them, even if they are the same. So approximately equal, well, they're immediately not equal. There is a difference, and then depending on your application, you might have to dig deeper to figure out what it is or not. But you will always have, right? Now, you know how instructors go and say, well, for us, everything is easy. So you just want to put an easy problem on the exam or something, and hoping that, oh, this is really cheap. It's going to take like 2 seconds to do this, and then you get the exams back, and you look at it and to grade, and it's just a massacre. So I'm going to give you an example that is of that caliber. Something that I don't have to think about at all, and turns out to be absolute. Now, we don't have time to do it in class, but you can enjoy this as a homework when you learn the rest. And then this might be the first problem we do in class next time, if you guys. So write this problem down and try it for homework. This was on one of the exams, and as I said, it was absolute massacre. Area between y equals sine x and y equal sine 2x. Now, when you graph them, you will immediately know where they intersect. You can use software to graph this, you can use your calculators to graph this, or if you know enough pre-calc 2, obviously, you will graph this immediately. So we'll start with this next time. Next time we'll cover at least 3 or 4 sections to make up for today.